Okay, so since I never get to see you guys in person, I'm gonna make a lovely little video. This was the section where the problems aren't actually terrible, but they are super long, so I filled in some of it already. I'm basically just gonna talk about the newer things or things you might not already know. So we're gonna graph some functions, and that means one thing that we have to do is figure out if there are any asymptotes. So if you think back to when we talked about asymptotes, you could have vertical or horizontal asymptotes. You'll have a vertical asymptote anywhere your function's undefined at. So if the denominator is equal to 0 somewhere, we're going to have a vertical asymptote. Oop, my pen's kind of thick here. Let me fix this. So if you look at this one, well, if I set my denominator equal to 0 and do some solving, cube root of 0 would still be 0. I'd end up with x equals -1 would make my denominator equal to 0. So my function can't ever pass through any points with an x-coordinate of -1. So we've got a vertical asymptote with an equation of x equals -1. Horizontal asymptotes are kind of what your graph trends towards as you go to like positive and negative infinity along your x-axis. So say that this is your graph, and it looks something like this. Maybe it's getting closer and closer and closer, it looks like, to y values of 2. That would be a horizontal asymptote. To figure out where those are, we would take the limit as x approaches positive and negative infinity. So if we do the limit of our function as x approaches infinity, 1 over x plus 1 cubed. Well, if you just kind of think about what's going to happen here, we have 1 over, if you're plugging in some very large value for x, some really big denominator, which essentially is going to go to 0. That means we're going to have a horizontal asymptote of y equals 0. If we approach negative infinity, it'd go to negative infinity in the denominator, but 1 divided by a really huge negative number is still going to be really, really close to 0. So horizontal asymptote of y equals 0. Okay, so besides asymptotes, if we're going to graph a function strictly using calculus, it's a good idea to have some important points, like any x or y intercepts. So we'll find those. Like I just did, we'll figure out our asymptotes. And if it's a polynomial, look at the end behavior. So like if you have an even degree polynomial, both ends should point up. Or you could actually take some limits as you approach positive and negative infinity and see whether they go to positive or negative infinity. We're going to figure out whether it's increasing, decreasing, concave up, concave down for our maximum and minimum values. And then we're going to do whether it's concave up or concave down. So a lot of this is review. The only thing really that we haven't done a ton of lately is this finding asymptotes, finding intercepts, and then just the whole putting it all together. All right. So like I said, some of this I already filled in. So if you want to find an x or y intercept of your function, if you're on the y-axis, you know your x-coordinate is 0. So if you like plug 0 in for both of those x's, you get that your y-intercept is going to be 0, 0. If you're on the x-axis, you know the y-coordinate has to be 0. So if you plug in 0 for your output for y, and I did a little bit of factoring, ended up with 2 x values that were x-intercepts. So there are 2 x-intercepts of this graph. We're going to go ahead and do our asymptotes or end behavior here. There won't be any asymptotes because it's a polynomial function, not a rational function. So there's no denominator that could be equal to 0 for a horizontal asymptote, or sorry, for a vertical asymptote. And it actually won't have any horizontal asymptotes either. We do know what the ends will look like if its highest degree term is 4x to the 4th. don't know if you remember this from Algebra 2 or not, but even degree polynomials, both ends either go up or down. And since it's a positive 4, we know that it's going to go up on both ends. I already did the derivatives that we're going to need for our concavity in our maximum and minimum values. So first and second derivative, find them if you don't have them. And then find your critical values to determine where it's increasing and decreasing. So set your first derivative equal to 0. Figure out what your critical values are. Break up your number line. And then plug a value in each of those intervals into your first derivative to test whether it is increasing or decreasing. And then since we knew it went down and back up, we're going to have a local minimum at 9/16, and we'd have to plug it back into the original to get your y value. So that you've done before. We've also done concave up, concave down, and your inflection points. Just take your second derivative, set it equal to 0, and get your critical numbers for your concavity. Those two are 0 and 3/8, so again, break up your number line, plug some values into the second derivative this time to determine if it's concave up or concave down. And it does switch concavity at 0 and at 3/8. Remember, if it doesn't change, then there is no inflection point. It does, though, so we get 2 inflection points at those coordinates. Okay, so putting this all together, I would start with any points that you have. So like x and y intercepts, maximum and minimum values, and inflection points. So let's get those plotted. 0, 0, and 3, 4, 0 are your x and y intercepts. We have a local minimum at 9/16, negative 0.1-ish, so 9/16, a little over 1/2. That's my local minimum right there. And an inflection point at 3/8 and a little bit higher than the point I just drew, so somewhere in here. This graph is going to be approximate, so don't worry about it being absolutely perfect. Okay, so what I would probably do is kind of work from left to right here. So if you look at what's supposed to happen from negative infinity to 0, it's supposed to be decreasing and concave up. Okay, so let's draw on that little section. Oh, oops, hang on. Get my technology in line. Okay, so coming down, decreasing, and concave up until I get to 0. Okay, my next little section is from 0 to 9/16. It's supposed to still be decreasing, and actually it stops at 3/8, sorry. From 0 to 3/8, it's supposed to still be decreasing, and it is going to be concave down. So switched concavity here, so it's decreasing, but now it's concave down, which is a little bit hard to draw. Let me zoom in here. So decreasing and concave down. So try and make it look like it's concave down there. Okay. All right. So I'm at 3/8. At 3/8, it switches to concave up. And it is still decreasing. Concave up should look like this. And now at 9/16, it's got to be increasing, and it's still concave up. So it looks like that. So it's got to go through all those points that you have on your graph. So you do have to connect them all, and it just needs to make sure that you have the right like shape. So I probably could have made that simpler if I just would have thought about it that way. If I'm like, oh, I have to connect all these points. And guess what? All you really need to look at is the concavity in that case. Is concave up till I get to 0. And then it's concave down, concave up, concave up. Boom. That was easier. Should have done that to start with. All right, another one. So if you look at this one, I already did your x and y intercepts again. So again, y-intercept, plug in 0 for x. If you plug in 0 for x, though, you get 0 in the denominator, so it actually isn't going to cross the y-axis anywhere. X-intercept, if you set it equal to 0 and do some solving, you get 2 x-intercepts at positive and negative 1. Asymptotes, okay, well, the reason we didn't have a y-intercept is because you have a vertical asymptote when x is equal to 0. For your horizontal asymptotes, do the limit as x approaches infinity of your original function. We can go back to divide everything by x to the third if you'd prefer. Or we could use L'Hopital's rule. Let's do that. More practice. Because this is of the form 0 over 0. Or no, it's not. It's of the form infinity over infinity. So we could do L'Hopital's rule and reevaluate our limit. Derivative, 10x, 3x squared. Those will divide out. Just getting you 10 over 3x. Well, as x goes to infinity, that denominator is going to be really big. So we're going to have 0 for our limit and y equals 0 for our horizontal asymptote. All right, derivatives I already did. They were messy. You guys know how to do derivatives, though. All right, figuring out where it's increasing, decreasing, maximum, minimum values. You guys got all that. Find your critical numbers, plug values back in to see where it's increasing, decreasing, and max and minimum values. You got that. It just takes a little while. Same thing with concave up, concave down, and inflection points. Okay, so let's talk putting it all together here. So looks like we've got some values around 2 and 1. Okay, no real huge values that we need to graph here. So I'm just going to count by ones. Okay. So again, I would plot all of the points that you know, which x and y intercepts. X-intercept at 1, 0, negative 1, 0. Inflection points at negative square root 6, which is about 2.5. And then negative 2.5, negative 1.7, so right about there. And then positive version, so positive 2.5, positive 1.7. Okay. Maximum and minimum values, negative square root 3 and negative 2 approximately. So negative 1.7, negative 2. Sorry, it's not going to be a perfect graph. And positive 1.7, positive 2, approximately. Okay. Also, asymptotes. Horizontal one of y equals 0, vertical one of x equals 0. Sketch those in here. So remember, your graph won't cross a vertical asymptote, but it can cross a horizontal asymptote, which it's gonna, because it's right on my horizontal asymptote already in a couple places. Okay, let's look at concavity. and increasing, decreasing to see what our kind of ends do here. So on the left side, it's decreasing and concave down until we get to our first point here. Whoops. And these are the only x-intercepts, so it can't actually do what I just did. I tried to draw it in like that, but it's not going to cross the x-axis anywhere except at these two x-intercepts. So it's actually going to stay down below this horizontal asymptote. So concave down and decreasing. Got it. And then it's going to be concave up. And still decreasing to get to that point. I don't know if that looks concave up or not. Should. There we go. That's better. Stays concave up. Stays concave up. Stays concave up. To go through those points, it has to be increasing anyways, but let's just check. Yeah, it was increasing from negative square root 3 to 0. Looks like that. Okay. On the other side of our vertical asymptote, we're talking concave down. So concave down. Ooh, that's going to be kind of weird looking. And it's going to be increasing. Okay, I see how this has to go. Okay, so concave down and increasing means it's got to look something like this. That's the only way it can be concave down. Okay, so concave down and increasing. And then it actually switches to decreasing but stays concave down. So it's going to look like that. And then I get to my inflection point and it becomes concave up and decreasing. Oh, it was already decreasing in between those two, but it becomes concave up and still decreasing, which means it has to look something like that. Can't cross the x-axis anywhere because we don't have any additional x-intercepts.